Hi everyone, today I would like to talk about the householder algorithm and also QR decomposition using householder. In the last videos, I talked about the Gram-Schmidt and how to do QR decomposition using Gram-Schmidt algorithm. And I also talked about the advantage and disadvantage of using Gram-Schmidt. So I talked about that Gram-Schmidt is a very easy algorithm to implement. It's very easy to understand. It's very intuitive. You can do it by hand. It has numerous applications to find the orthonormal basis functions, to find whether set of vectors are linearly independent or not. However, I also mentioned that Gram-Schmidt is not robust because of many multiplication and addition. It's not really recommended for floating point operation. So if you go to your numerical packages or softwares like MATLAB, Python, or R, when you want to perform the QR decomposition, the chance is that they will not use the Gram-Schmidt algorithm. They are using householder or variation of the householder. Okay, so in this video, we want to understand the concept behind the householder and how we can actually achieve QR decomposition using householder algorithm. Okay, now, first, what is the idea behind the householder? So assume that I have this vector x here, right? And I have this hyperplane P. In 2D, it's just a line, right? I want to find the matrix in such a way that when I multiply the matrix by this, so perhaps I can make this hyperplane H, right? Even H is not a good name because of the householder, maybe G, right? I'm looking for a matrix P, such as like a projection matrix, that when I multiply by this vector X, right, I get some sort of a reflection of vector X respect to this hyperplane G, right? So when I multiply this matrix P by this vector X, I will get some vector C here in such a way that the distance of X to the hyperplane is the same as distance of C to this hyperplane. So we call this type of transformation a mirror transformation. What I mean by that is that this distance A from here to here is the same as distance from here to here, B, right? So A is equal to B, okay? And also sometimes we call it reflection about the hyperplane, right? So sometimes the householder operation is called a reflector, okay? And this is the idea. Now here we have a vector x and then hyperplane G. So let's define this U is a unit vector which has a norm 1. The norm 1 is orthogonal to this hyperplane. Okay. So as I said in the 2D, the hyperplane is just a line. So this vector U has a unit norm, is a very important constraint, and is orthogonal to the hyperplane. Okay, so I would like first to find this vector C. Let's take a look at how we can do that. Let me just do live. If I go ahead and connect this line from here and look at this rectangle I have, I'm trying to find this A, right? This A is like this. It's pointing upward. It's a vector. Now, this A is nothing but the same as this vector here. But this vector is nothing but projection of X on the vector, unit vector U. But what is the projection of X on U? Let's have a little note here for ourselves. We have a note. Projection of A on B is nothing but A dot B, norm of B squared dot B times B. But again, the B here is U, but U is a unit norm vector. So this one is 1. Therefore, what we get is X dot U. For our problem here, this projection is nothing but X dot U times U. Okay, so if I find this quantity, this is equal to A, right? Because we form this rectangle and the sides of the rectangle are the same. So this A is the same as this one. Okay, now, but wait, I'm trying to find this vector, right? Because I know B also is the same as this, and I want to get to the vector C. So this vector, I call it A prime, is nothing but the vector that has the same magnitude as A, but opposite direction. So what is A prime then? A prime is negative projection of x on u, okay? Negative projection of x on u. So negative projection of x on u. The x projection on u already has a u included. You don't have to multiply u. Okay, good. But what is b? B is nothing but a prime. Why is that? Because that was our claim. That was our assumption. We said that I'm looking for a projection in such a way that the distance of the vector x, the orthogonal distance of vector x to the hyperplane G is the same as orthogonal distance of vector C to the hyperplane G. So A and B have the same magnitude, right? Or A prime and B are exactly the same. They have the same magnitude, have the same direction. Okay, so what is B as well? B is equal to A prime. So wait, then what is this quantity from here to here? This quantity from here to here is nothing but negative 2 projection of x on u. Okay, therefore, so here I wrote that as well. B is equal to negative projection of x on u. You don't need times u, you don't need that, right? Because the projection itself has that times u. And then c, the vector c is nothing, this vector c is nothing but x minus 2 projection of x on u, right? This vector c is nothing but x minus 2 projection of x on u. Okay, now at this step, you're gonna go ahead and write the projection x on u based on the equations that we know. Okay, so this is the equation of the projection of x on u. The reason why the denominator is 1 because u is a unit vector. Therefore, the vector c is nothing but x minus. Okay, so let's see. This is x dot u, the dot product of x and u times the vector u, right? So according to the property of the dot product or definition of dot product, we know this quantity is nothing but x transpose u or u transpose x. Keep that in your mind, okay? So we get x minus here 2 times u transpose x, right? It's u dot x, inner product of u and x is u transpose x times u, okay? Good. Now, let's see what happened that from this step, I get to this step. So we know that u transpose x is a number. That's why we call it a scalar product. It's a number. Okay. Now, this is a number. Consider it to be, for example, I don't know, 5, 4, 6, right? But this is a vector. So recall that when you multiply a scalar alpha by this vector x1, x2, all the way to xn, you could write this one as a vector x1, x2, all the way to xn times alpha. Doesn't matter which side you're multiplying alpha to, right? Okay. So I'm gonna, you see the u is multiplied by this x, u transpose x. I want to bring u to the, from this side is multiplied by in the right. I want to bring it to the left, right? So what I can do, I can write the intermediate step here. I can write this one as 2u, u transpose x. I can do that, right? Okay. Now the step is very easy. Now what I'm going to do is group these two together, right? So I'm gonna get what? I'm gonna get 2u transpose times x. And this is exactly what I have. Okay, so c is equal to x minus 2u transpose times x. Now wait, we want to get a matrix that project x or transform x to c. Okay, so what I'm going to do, I'm going to write one more step. C is equal to, I factor from x, right? I get identity minus 2u transpose, okay, times x, right? Now, this is a matrix. Remember, this is a matrix. Why is that? Because I'm subtracting identity from another quantity, right? If in order for this subtraction to make sense, the other quantity also should be a matrix with the same dimension. So this is a matrix, okay? Now, let's call this matrix P. This is called a reflector or projection transformation matrix, right? That what it does is that it reflects the vector x about this hyperplane G, right? In such a way that the distance, the orthogonal distance of the vector x to the hyperplane G is the same as orthogonal distance of this vector C to the hyperplane G. Okay, so this is a vector, that's a matrix P that we are looking for. I wrote it here for you, that is called reflector. So matrix P is a transformation of vector x with respect to the hyperplane perpendicular to U, which U is that unit vector, right? There are two ways you can define that. U is a unit vector that is perpendicular to the hyperplane G, or hyperplane G is the mirror that is perpendicular to the unit vector U. Okay, good. So now P, this transformation that we find, this P is equal to I minus 2 UU transpose, is called the reflector or householder, and hence the name householder. So householder name is coming from this transformation that we just saw. Now let's take a look at some properties of a householder matrix P. Now, first of all, the householder P, matrix P, is symmetric. It's very interesting that P transpose is equal to P. Why is that? Why is that? So if P is equal to I to UU transpose, then what is P transpose? Well, I transpose is I, because I only has a non-zero element on the main diagonal. Right? Transposition doesn't really change the elements on the main diagonal. I. But now what is, so 2 doesn't change, but U transpose. Let's see, U transpose, right? So what happens is that this U transpose comes first. We will have U transpose, and U transpose. So what I get is that I get I minus 2 U transpose is U transpose. So P transpose is the same as P. That's a very interesting property. So it's symmetric matrix. But perhaps the most important one is not this. The most important is the second one. The householder matrix or the reflector matrix is orthogonal matrix. Is a square, remember, a square, and the P transpose P is equal to identity. So it's orthogonal matrix. Why is that? Let's take a look at that. We know it's symmetric, so P transpose is the same as P. So we write the P transpose is the same, and let's just multiply them together. I times I is I. I times anything is really the same thing. I times negative 2 UU transpose is negative 2 UU transpose. And then we have again another negative 2 UU transpose because of this. Now let's multiply these two together. Okay. So I'm gonna multiply it again. You guys see this? I'm gonna multiply it again. You get 2 times 2 is 4. You get U transpose, U transpose. But wait. What is this quantity? U transpose U. U transpose U is nothing but norm of U squared. But this is equal to 1. Right? So what I get is I, this quantity and this quantity becomes negative 4 UU transpose plus 4 UU transpose is becoming identity. So matrix P is an orthogonal matrix. Now you see the relationship why we are going to use it in the QR decomposition. So first we have to actually go over all this introduction to see what is the application of this matrix P. Okay, so it's an orthogonal matrix. Remember, recall the definition of orthogonal matrix. It must be a square, and the matrix transpose times the matrix itself should be identity. If the matrix is not a square, we don't call it orthogonal. Right? I talked about that in the orthogonal matrices video. If the matrix is not a square, but the P, like A transpose A is equal to identity, we call it the matrix with the orthonormal columns. Okay, good. So P is an orthogonal matrix. Now that we know how to find the P, now the question is how can I find U? If I find P, if I find U, I can actually find P as well, right? All I need to do is just put it in this equation. We know P is orthogonal, we know P is symmetric, but the question is how can I find U? Once I find U, then the problem is over. Okay, so here I wrote a little bit of explanation that by choosing a vector u carefully, we can map vector x to any direction we like, right? It's a projection. We can map it to any direction we like. So once you find the u, automatically you find the hyperplane as well, because u is orthogonal to the hyperplane. Now, let's see how to find the u. Now, in order to have a good idea how to find the u, here we need to have some knowledge as what we want to do with this u.